here, Perali, Capone, and Seigo. So I think we have 5 or 2 minutes each, between 2 minutes and 5 minutes each, and just make your points like.
I think it's already time to say good afternoon. It's a pleasure.
Nothing wrong.
Yeah, it's just 12 o'clock. I think certainly I will agree with Giancarlo that experiment is driving this field. We know about discovery, and this was great times that we could start working more on strongly correlated systems. I think nowadays we fully appreciate the complexity of correlated oxides with many different types of order and interrelations between them. And these are real challenges for all of us to investigate this. And we know now that certainly all different degrees of freedom play a role: spin, orbital, lattice, and charge in various phenomena which are observed. And it is really important to treat them properly. In particular, frustration is also important, and it is out of this frustration, I think, that new phenomena can arise, like, for example, due to competition between the kinetic energy and magnetic energy. We have stripes, we have also stripes in other systems with orbitals, and all that arises because we have these different trends, and in nature they manifest themselves in a form of self-organization. Moreover, frustration got a new context here, I think, because it's not only frustration on frustrated lattices for spins or intrinsic frustrations in orbital models, but we also have charge frustration on frustrated lattices. So all that becomes important and should be considered seriously. Concerning spin orbital systems, I think more and more we realize that entanglement is important, and there are 2 kinds of entanglement: entanglement on site due to the spin orbit coupling, and also on bond entanglement, which is within the super exchange interactions, and there is certain interplay between them. This is very interesting to investigate, but I think it also brings us to think about some new methods to treat entanglement, because this is not so easy to treat. Of course, one can do exact diagonalization, but we need to perhaps to contemplate a bit more and develop new methods in this theory. And finally, I would like to mention one aspect which was not discussed so much here, I think, but of course I could only see part of the meeting because there were parallel sessions, but nevertheless my impression was that oxygens were not treated in extenso, and certainly in all these oxides we have oxygen holes, like in this angarized singlet, and also in more complex situations it would be interesting to see how the oxygen degrees of freedom play a role, and what they can change, how they manifest themselves in experiment. I think with this I would like to close my statement, and we are all very grateful to Antonio for providing the opportunity to discuss the complexity in correlated oxides.
Okay, I think you have already said everything. So let me just start by mentioning that this series of conferences has evolved from these old phase separation workshops beginning of the 90s, where the community was very small, believing that electronic inhomogeneities play a significant role in the cuprates. Meanwhile, it's a well-established fact, and I just wanted to say some words on the charge-sensitive waves, which are now observed essentially in all the cuprate materials. So, at the beginning was the experiment by Tranvada on the stripes in the lanthanum barium carboxide, but now we know this is a charge-sensitive wave is a generic phenomenon in YVCO, in mercury, thallium-based compounds. It's not clear whether this is, well, apparently from the experiment there are differences concerning, for example, the incommensurability as a function of doping. There are differences that the spin is not apparently involved in the charge-sensitive wave in this YVCO. But for theory, it's of course, and also the experiment, it's necessary to investigate what is the link, or if there is a link to superconductivity at all. What could be, I mean, there are proposals which say there is a quantum critical point, which then the fluctuations drive superconductivity. There are proposals that this is Josephson coupled pair density wave, but so there more work has to be done in order to link these orders, which are these charge sensitive orders to superconductivity. Want to finish with some interesting thing. I think that theory has up to now too much focused on just simple models which involve the carbo-oxygen planes in these materials, and it becomes more and more important, I think, to take out of planes degree of freedom into account. This was interesting to see that also in these resonant X-ray experiments, the charge density wave order has strong dependence on the perpendicular direction. So I think this is a future direction one should follow to incorporate more the out of plane degrees of freedom in the theory.
Okay, so during this conference, it's a really incredible conference, we have seen that in several talks that different superconductors and superconductivity have been realized under extreme quantum confinement and extreme conditions. And we have seen that starting from materials in which the critical temperature is quite low, we can arrive, if we're able experimentally to find the correct degree of freedom, we can arrive to very high critical temperature. And so we have seen experimentally that critical temperature can be amplified, and the penny strength can be something that at the end we will be able to control. And so I think that this is very important, because we have now finally we can see that our dream to arrive in some way to very high or even room temperature superconductivity is not anymore only a dream, but it's becoming a realistic project. And a realistic project that we can communicate to the younger generation, because this will be really an important point for future investigation, for technological application, and to have finally an impact with superconductivity. And so, even though this kind of reasoning is very general and should be really, I mean, very difficult to enter in details of these new novel directions. I think one of the aims of the next conference will be really to involve more younger scientists in order to start with them novel projects. And I would like to add also that the story of the BCS-BC crossover is very important in helping to find higher TC, higher superconductivity with a higher critical temperature. Because once we realize that also, for instance, in iron chalcogenides or in different other kind of iron-based superconductors, we realize that it exists a pairing temperature scale. We have seen some beautiful experiments during this conference demonstrating the existence of fluctuating Cooper pairs above the critical temperature. So it is very important to control the strength of the pairing because it can increase the energy and the critical and the temperature scale for the onset of Cooper pair formation. So what we should learn in the future is not only how to control the pairing and to increase the pairing, but also how to contain, how to suppress or to take as less as possible the critical fluctuation, the quantum and thermal fluctuation, which usually in all the superconductors we have seen bring the pairing temperature T star down to the critical temperature. So we have another degree of freedom, which is very difficult to control both experimentally and from a theoretical side. But if we were able to work on these two different energy scale and degrees of freedom at the same time, we can really help this project to get finally good temperature superconductivity with us. It's a realistic dream now. This is my point.
Okay, thank you for such a very nice round table, and I think it's three different point of view by Andrei Olesh, Getz Seibold, Andrea Merali on the physics that is very inspiring for new development of this debate. Thank you for your. Now we have the last round table with Ronald, Usnets, Xenofonto. Okay, the last round table is by Professor Roman Kuzniak, Xenofontov, Alessandro Ricci, and Ronald. Okay.
I have two general comments. One comment concerns a conference, and second comment concerns the scientific part of the conference. So, concerning the conference, this is my second conference organized by Antonio, and I found significant progress. For me, this is my feeling that at this conference is more scientists from the United States. It is important, but the most important is there's much more scientists from China. And the Chinese science is developing very fast. So it is, if you compare China 4 years ago and now, it is incredible change. So I am very happy that Antonio realized this and he just invite quite many scientists from China. I think that it will be future. So it is general comments about the conference. Concerning scientific contents, I am very happy that there is many of experimental presentation and the people try to introduce new superconductors. I am under impression, for example, two presentations from Switzerland where people show how you can apply average pressure to grow several superconductors. Of course, the most important it is if you apply extreme, because you can probably get absolutely new material. But even if you apply like anvil pressure cell or something like this, you can make new materials. So I'm